So, as Kirby mentioned, I'm going to do a paleoclimate reconstruction on lake sediments from Abbott Lake, California, and that's Abbott Lake, super pretty and green. To give you an idea of what we're going to talk about, first we'll go a little introduction into Abbott Lake and the project's objectives and hypotheses. We'll go a little into the background about Abbott Lake in the modern climate setting, a little bit methods, results, discuss some of the main issues that our project addresses, and then finish with some of our main findings. Now, a little bit of background. The coastal southwestern United States, shown by the purple region here, is a highly populated region, and it's dominated by winter precipitation. And because we have this high population growth rate and a unimodal hydroclimate, this region is and will continue to be freshwater poor. Therefore, we want to understand past hydrologic variability to better assess future water resource limitations. Now, currently, there are limited paleoclimate records in Southern California. They're shown by the blue dots. And you can see that there's this gap in the coastal central California region. But our site, Abbott Lake, fills this gap and allows us to extend the knowledge of hydrologic variability along the coast of California. In addition, this region is characterized by a north-south hydrologic dipole. And this figure here is kind of showing you that. So what this figure shows you is the relationship between precipitation and tropical Pacific Ocean sea surface temperatures, which serve as a proxy for ENSO. So essentially, we're looking at the relationship between precipitation and ENSO. And when we do so, we see that we have this dipole, which is this right region right here, and that when we have El Nino, areas south are wet, while areas north are dry. And when we have La Nina, areas south are dry, while areas north are wet. So opposite reactions to the same event. Now on the next slide, we're going to go over the spatiotemporal variation of this dipole. And this gray box here highlights the region we're going to focus in on, which extends from 50 to 35 degrees north latitude. So if we zoom in on this area, this figure is from a study on the dipole by Wise, 2010. And we have latitude on the Y, we have years on the X. This bold line right here represents the latitudinal position of the dipole. The dashed line represents the latitudinal position of Abbott Lake, so you can see in relation. And you see that the dipole has about an average position of 41 degrees, but it's not stationary. It has a modern range of about 37 to 42 degrees during this time span. But more interestingly, we see that for about 10 years right here, the dipole shifts 3 degrees south. Now that doesn't seem like a lot, but that equates to about 333 kilometers. That's a huge distance for that dipole to transition to. And if we look, it gets significantly closer to Abbott Lake, which suggests that maybe if we look at longer time scales than Wise did, that maybe that dipole even surpassed Abbott at times. Now the position of the dipole is influenced by the Pacific Decadal Oscillation, or PDO, such that when we have positive PDO, that boundary shifts north, and when we have negative PDO, the boundary shifts south. In addition, the phasing of PDO and ENSO, or El Nino Southern Oscillation, influences the strength of the dipole. So when we have positive PDO and El Nino conditions, the dipole is more defined between those two regions. And when we have negative PDO and La Nina, the boundary becomes a little more fuzzy or weakened through time. If we look back at this map, again, the blue dots represent previous sites that are done in Southern California. Abbott Lake is the red star. We now have this shaded gray box, and that's from the modern transition zone of that dipole, according to Wise's figure that we just saw, that extends from 42 to 37 degrees north latitude. If we look, we see that Abbott Lake is significantly closer to this transition zone in comparison to our previous sites, which allows us to extend the spatiotemporal knowledge of the hydrologic dipole. But the question is, why do we care, right? Why are we going to spend our time studying the position of the dipole? Well, the thing is that the dipole's position dictates how much precipitation a region receives based if we have El Nino or La Nina conditions. And if we can better assess how much rainfall a certain region receives during those different phases, we can better assess future water resources, which is really important here in California. As you guys have probably heard on the news, we have this major drought, right? So that could help us out. So with this, we really have three main objectives. The first is we want to construct hydrologic variability at Abbott Lake over the past 2,000 years, since it's never been done before. The second is to assess the spatiotemporal variations of the north-south hydrologic dipole that we discussed. And the third is to figure out the forcings that drive the hydrologic variability we see at our site. Our first hypothesis then is that we'll see a dry medieval climate anomaly that transitions to a wet little ice age. We will see that the dipole is not stationary. In fact, it will have latitudinal variations through the late Holocene. And this will be evident by comparing Abbott Lake to two records, one that's always north, Castor Lime Lakes, and one that's always south, Zaca Lake, and comparing the phasing of all three. And lastly, that Pacific Ocean atmosphere dynamics, such as ENSO or PDO, are driving the hydrologic variability we see at our site. All right, so a little bit about Abbott Lake. Abbott Lake is in Monterey County, California, in the Santa Lucia Range, shown by the red star. And it serves as one of few natural lakes between the coastal Southwest and Central California. In terms of its geology, the purple represents igneous rocks. So the western side is characterized by igneous. The eastern side, or the orange, is characterized by sedimentary rock, specifically friable sandstone. Formed as an oxbow lake when the Arroyo Seco River transformed from a meandering to a braided stream and then got cut off, thus forming an oxbow lake, what we now know as Abbott Lake. In terms of its dimensions, the light blue region here shows you the maximum potential extent of Abbott Lake, which is about 0.46 kilometers in length or 0.08 kilometers in width. The dark blue here shows you the modern extent of the lake, so a little bit smaller. It sits in a small drainage basin. It's about 0.75 square kilometers, and it's pretty steep. It has two main sources. Oh, it's also a closed basin lake, which is important because that means that all lake level changes you see are due to precipitation evaporation ratio changes, which is important for paleoclimate studies. And there's really two main sources of water. The first is direct runoff from steep-bound mountainsides when we get precipitation, and the second is possible groundwater seepage. Now, two things to note here on the Eastern Valley. There's evidence for incised channels that used to connect to Abbott and serve as inlets, but they no longer connect to the lake. And over here on the western side, there's an incised channel that connects Abbott to a dry lake that's down valley. But there's no, and when it's really wet, Abbott would overflow into the dry lake. But there's no evidence for recent flow, and there's been human modification to the channel. Now, Abbott Lake is relatively shallow. When we went in April of this year, the central basin, which is the deepest portion, was about 2 to 2.5 meters. But there is ample evidence to suggest that Abbott Lake was much deeper in the past, and therefore a much more significant lake than what it seems today. The evidence for this includes the presence of tufa and raised rocks on the south side of the lake, which form in the presence of water. The second is the presence of aquatic fauna in raised leucostrian sediments on the north side, specifically gastropods. And the third is this prominent tree line that characterizes the south side of the lake. Now, when we went in April, we wanted to see exactly how deep Abbott Lake could be. And the reason for this is if we're going to say that Abbott's deep or shallow X amount of years ago, well, how deep or how shallow are we talking about? So we took several measurements from the tree line to the modern lake surface, because we know the lake used to be at that height. And we did so at all these yellow dots, so 6 different sites. In the central basin, so sites 3 through 6, the tree line to the lake surface was 4 to 5 meters. And if you account for the present body of water, that means that this entire region here is about 7 to 8 meters. So in the central basin, it could fill up 7 to 8 meters before it spills over. On the eastern side, so at sites 1 and 2, the tree line to the modern surface was only 2 to 3 meters, so significantly shallower than the central basin now. But if we account for the core we took, the core was about 5.5 meters. So if you take 5.5 meters plus that 2 to 3 meters, that means at the base of our core, thousands of years ago, that Abbott Lake could have been 7.5 to 8.5 meters, so much deeper. And this huge volumetric loss we see at Abbott Lake over time is because we have a rapid sedimentation rate, because we have this friable sandstone bedrock that characterizes the drainage basin. And the site gets these large magnitude storms that washes in, brings lots of precipitation, runoff, and thus kind of filling up our lake. Now, the modern climate is characterized as Mediterranean, which means we have cool, wet winters and hot, dry summers. But as I mentioned before, it's unimodal, and only winters matter. Summers don't really matter here. But we wanted to look specifically at some precipitation trends. So we did 2 comparisons. The first was a comparison between D, E, and F, which is at Big Sur, Paloma, and King City. And the second comparison was along the coast from D all the way down to A. And we wanted to see how precipitation changes across these two directions. And when we did so, we found two trends. The first, when we compared D, E, and F, we found that precipitation decreases from the coast as we go inland due to a rain-shadow effect. And the second is that precipitation is highest in Central California and decreases to the south. Now, why that's important to Abbott Lake? Well, Abbott Lake sits in a completely different location than the previous paleoclimate sites, which again are the blue dots. And it also is characterized by a different hydroclimate. We see that it has much wetter winter climate regime than those sites. And climate change is not consistent spatially. It changes over time. And so we need to characterize this region specifically rather than just assume it's the same as those more southern sites. Precipitation now is driven by two main mechanisms. The first is El Niño Southern Oscillation, or ENSO, which measures tropical Pacific Ocean sea surface temperature anomalies. And there's two main modes. There's El Niño and La Niña, which you guys have probably heard of. El Niño on this graph is represented by the red when we have above average temperatures in the ocean. The blue represents La Niña when we have below average temperatures. And you can see that their two phases oscillate, and they oscillate about interannual variability from 2 to 6 years. The second mode is Pacific Decadal Oscillation, or PDO, which measures sea surface temperature anomalies in the North Pacific. So ENSO is tropical, PDO more of a northern forcing. And again, there's two different modes. You have your cold, or you have your warm or your positive PDO, which is the orange when you have above average temperatures. And you have your cold or your negative PDO, which is represented by the blue when you have below average temperatures. Again, you see the two phases oscillating throughout. However, they don't oscillate at the same frequency as ENSO. They oscillate about interdecadal variability rather than interannual variability. Now, the phasing of ENSO and PDO is what determines if we have dry or wet winters in this region. When we have wet winters, we attribute it to a positive PDO and El Niño, which essentially weaken the high pressure system we have off our coast, allow the jet stream to drop further south, which brings more storms in our direction. El Niño brings in more subtropical moisture, so not only do we have more storms, but more moisture for those storms to tap into. Dry winters is attributed to a negative PDO and La Niña, and what happens is the phasing of those two strengthens that pressure system off our coast, pushes the jet stream further north, so we get less storms. And La Niña pushes the subtropical moisture away, so even when we do get those intermittent storms, they don't really have the moisture to tap into as when we do when we have El Niño. All right, so enough about the background, into the fun stuff. So to test the hypotheses, we took 6 reconnaissance gouge cores, which are shown by the black dots here on the map. Gouge cores are simply sediment probes, which allow you to quickly, easily core to see where you want to core and what kind of coring equipment you should use based on your sediment type. Of the 6, gouge core 5 was selected as our primary coring site because it had the thickest sediment sequence. And so from the red star, by gouge core 5, we took 2 sediment cores. The first was taken in January of 2013. The second was taken in October of 2013 from the same location to extend that record. Once we had our cores, we took it to the lab where we then opened them and we were able to describe them. And then we sampled them and ran magnetic susceptibility, LOI 550 for organic matter, LOI 950 for total carbonate, grain size, microfiscals, and statistical analysis. We also took 9 discrete organic samples for radiocarbon dating, the location of which is shown by these red arrows here. And the location of them was determined either from key events we saw in the core or where discrete organics were visually abundant. And we took all 9 samples and took them to UCI for radiocarbon dating. So this is the table showing you the results for them. Of the 9, 3 samples were dismissed. The first 2 were charcoal, which are highlighted, at depths 278.5 and 289.5. And the reason the charcoal was dismissed is if you look at the radiocarbon years, they're significantly older than the bounding dates, which tells us that they're stratigraphically out of place, and therefore, based on law of superposition, we discarded them. The third one was this gashapod, and so we took the gashapod at the same depth we took charcoal. And the reasons for this is we wanted to be able to date gashopods where we didn't have charcoal or other kinds of discrete organics. But the thing is, gashopods can tend to take in old carbon. So we wanted to calculate the reservoir effect using the comparison here. However, we had to throw out the charcoal we were going to compare it to, and we don't know the reservoir effect, so we had to throw out the gastropod as well. So not as helpful. That left us with 6 radiocarbon dates, which are highlighted in blue or purple, or whatever color that looks like to you. And then we put those 6 dates into a program called Bacon. And Bacon then constructs an age model for you. And what it does is it converts your radiocarbon dates to calendar years BP, and then breaks your sediment core into 5 centimeter thick sections and calculates the sedimentation rate for each section, rather than assuming a constant accumulation rate. And it does so through millions of iterations. And then yields an age model that looks like this, kind of funky, but kind of cool. And so you have calendar years BP on your Y, and you have your depth on your X. The blue arrow here represents the top of the core, which we assume to be modern. The 6 purplish blobs are our dates, and they look kind of funny. So usually in age models, dates are single points, but Bacon recognizes that your radiocarbon dates usually have high asymmetric radiocarbon age distributions. And so,
No.
I was going to say bless you, and then it wasn't. Anyways, okay. And so the Y direction shows you the age distribution for each different date, and then the length in the X direction shows you the probability distribution of it being that specific age. And then the gray fuzziness is a 95% confidence interval after those millions of iterations were run. And together, these 2 cores span about 2,000 years total. Once we had our age model, we then constructed a composite core, or a master core, so we didn't have to work with 2 separate cores. To do so, we cross-correlated the 2 cores using visual wiggle matching. We did so for each of our different measurements, and we chose the measurement that had the most compelling correlations, which was total carbonate, which is shown here, and the peaks we correlated are shown by the red numbers. And then we'll use the total carbonate data to clip it into one master core, which we called the composite core, 13PC1. We then did so for each of our different measurements, which are shown here. We have depth here on our Y. We have all of our different measurements. The red arrows here represent the 6 ages we inputted into Bacon. So we have Chi, or magnetic susceptibility, organic matter, carbonate, and our 3 main grain size fractions, clay, silt, and sand. And because I'm going to go into it later, I won't go into it now, and I'll hold you into suspense for a little bit. All right, so the next thing we looked at was gastropods. And gastropods, we were able to identify 6 different types, thanks to Dr. Saxon Sharp at the Desert Research Institute, who identified the gastropods for us. 3 were identified to the species, 3 were identified to the genus level. And of those, we wanted to find 1 permanent aquatic species. And the reason for the analysis on the shells, we wanted to make sure that those isotopic changes are due mostly to changes within the water rather than the atmosphere. And so of the 6, we found 1 winning combination, which is gastropod B, formerly known as, and I'm going to butcher this, Gyralis parvis. But from here on out, we're going to call him Mr. GP, because I don't want to say that a bunch of times. So GP. So he became our sole aquatic species in our core. And so we plotted the GP data with our other graphs. And so we have the presence and absence of GP, so P being presence, A being absence, as well as our isotopic analysis. So this is a huge amount of measurements, a lot of data to be thrown at you, and it's hard to figure out where you want to start and what it all means. And that's where multivariate statistics comes in. And thanks to Dr. Nicole Benuso, we're able to run stats on our data to figure out where we should start and kind of what it all means. But the thing about stats is that you have to use measurements that have relatively the same resolution. And so we only used the measurements that are highlighted because they have nearly the same resolution. We didn't use the GP because it was sampled at a much lower resolution. So we ran 3 tests. The first was called cluster analysis, which groups your samples based on similarities and allows you to do so objectively rather than subjectively if you were to do it yourself. And so what it does is it takes all of your samples and measures the distance, called the Euclidean distance, between the samples and creates this dendrogram or tree-like structure. So we have our samples on the bottom, the different Euclidean distance. We chose a distance of 3.55, which is highlighted by the red dashed line, which told us that we have 6 groups in our samples. 1, 2, 3, 4, 5, 6. And we chose that distance so that we didn't overgroup or undergroup our record. We then ran analysis of similarities, or ANASIM, to test if those groups are statistically different or similar. And the ANASIM yielded an R-value of 0.849. And because that's really close to 1, we were able to say that the groups are statistically different. But to further test it, ANASIM also yields pairwise tests between each of the different groups and yields a significance level. A high significance level means those groups are more similar. Lower means they're more different. 12 of the tests shown by the blue confirm that there's a statistical difference, which is good. That's what we wanted. 2 did not, though, highlighted in red. They have a higher significance level. And so we took a closer look at those 3 groups, and we determined that they only contain 4 values, of which are these high atypical magnetic susceptibility values. So it makes sense that they're similar. And then this last one, between 4 and 5, we couldn't run because they only have 1 sample in each group, and you need at least 2 or more. The last test we ran was principal component analysis, or PCA. And what this does is further confirm if there's a difference in your groups, but it also tells you the dominant sediment signal or measurement at your site. And so how PCA works, I'm going to explain it a little bit. Because we're taking all these different measurements, instead of just plotting it in 2 dimensions, it first plots it in 3D, and then measures all the different directions in which you have variance or your data spread out. And it labels each of those different directions principal component axes. Principal component axis 1, or PC1, has the most variance, PC2 has the second most variance, such forth. And then plots it in 2 dimensions so you can more easily visualize it. So we plotted PC1 versus PC2, since that tends to show the most variance in your data. And as of right now, the axes have no meaning, so we don't worry about that. The black lines here represent the different measurements, and the different colored symbols represent our different groups, which are shown in the key above. All right, so now that we know a little bit how it works, we see that the groups are separated into well-defined clusters. We have group 1, blue, group 2, yellow, 3, 4, 5, and 6. And if we look at the first axis to see what's going on, we see that it's controlled by grain size. We have sand on the left, which means, back up a little bit, the closer a sample plots to a proxy line, that means it's more controlled by that proxy or that measurement. And so since sand plots on the left, that means that groups that are more on the left are more influenced by sand, such as group 1. And on the right, we have silt clay, so that means groups that are further to the right are more influenced by silt clay, such as group 3. Groups such as group 2, where they're more in the middle, are not really pulled in either direction. What PCA also does is produce these eigenvalues, which are shown in the table, and that tells you exactly how much variance is explained in that direction. And what we see is PC1 accounts for 55.7% of the variation in the data set, so a fair amount. We then looked at the second axis to see what's going on, and we see that it's controlled by magnetic susceptibility, carbonate, and organic matter. Same concept. As the further up on the graph the samples are, they're more influenced by carbonate or organic matter, such as groups 1 through 3. The further down on the graph, they're more influenced by chi, or magnetic susceptibility, so groups 4 through 6, which makes sense because those groups 4 through 6 are those 4 atypical values. And the eigenvalues tell us that that axis accounts for 25.1% of our variation. So still a fair amount. So what this tells us all together is that grain size is the dominant sediment signal, followed by total organic matter, total carbonate, and magnetic susceptibility. But we can't forget about GP. Although he wasn't run in the stats, he's going to prove to be useful, so don't forget about him quite yet. All right, so now we have all of our results in, and it's time to make sense of what it all meant. But the thing is, you can't directly measure hydrologic conditions thousands of years ago, so we have to implement what we call proxies. Proxies are a substitute for something we cannot directly measure, and luckily the physical and chemical analyses we run could be useful paleoclimate proxies for things such as fires, runoff, lake level changes, productivity within the lake, as well as epiluminant temperatures, which is just the water temperature near the surface, so the upper part of that water column. But the thing is, proxy interpretations vary site to site. They're not always consistent. They can tell you different things. And because of that, we have to look specifically at what the measurements mean exactly to Abbott, rather than just assume they mean certain things from other studies. To do so, we looked first at gastropods. And again, our focus is GP. And GP permanently inhabits shallow freshwater environments, such as marshes or oxbow lakes like Abbott. And because of this, previous studies have used the presence and absence of GP as a relative indicator of lake level, such that when GP is present, a shallow lake's inferred, and when GP is absent, they infer a deep lake. So we applied these interpretations to Abbott, and we said that when GP is present, it's shallow, and when GP is absent, it's deep. We then could compare our different measurements to the GP record to see what they meant. And the first one we compared GP to was grain size. And the reason is that the stats told us that that's our dominant sediment signal. And so grain size, the distribution of grain size, tells us a lot about the energy of the erosional processes, such that when we see larger particles, it means a higher transport energy because it takes more to move those particles. And smaller particles means a lower transport energy because it takes less energy to move those particles. So to illustrate this, research was done on 20 rivers throughout Southern California. And what they found is that when precipitation was higher, river discharge increased because you have more water in the system. And because of this higher transport energy, more coarse grains were mobilized. Therefore, previous studies in Southern California, such as Kirby's work at Abbott Lake and Lake Elsinore, have used variations in sand content to infer runoff variability, such that when they see high sand, they infer more runoff. Low sand, they infer less runoff. And we wanted to use these same interpretations at our site. But again, we can't just assume that they hold true, we have to test them. So we compared our grain size to the GP record, and we found that when we have high sand when GP is absent and a deep lake's inferred, and low sand when GP is present and a shallow lake's inferred. Therefore, we said that runoff, our grain size can be a proxy for runoff, such that when we have high total sand, it means enhanced runoff and higher lake levels. We see low percent sand, it means reduced runoff and lower lake levels. However, the relationship between the two is always not 100% true. There's some parts where it doesn't always match up, but it matches up enough to give us confidence that it is a reflection of the runoff variability. We also broke the grain size into 5 different size fractions and compared it to the GP record to see maybe if a certain grain size fraction better explains the hydrologic trends we see in our record. And when we compared it, we found that coarse to very coarse sand showed a strong relationship to GP, such that when GP is absent and a deep lake's inferred, we see lots of coarse sand. When GP is present and a shallow lake's inferred, we see little to no coarse sand. And because coarse to very coarse sand takes a higher transport energy to move, right, because they're super large particles, we're going to say that percent coarse sand tells us the magnitude of how wet it is. So total sand tells us wet, dry. Coarse sand tells us relatively how wet it was. We also looked at total organic matter, and when we compared it, we saw that we have low organic matter when GP is absent and a deep lake's inferred, and we have high organic matter when GP is present and a shallow lake's inferred. Now, organic matter can either be derived within the lake or outside the lake, and based on where it's derived, it can tell you either productivity or runoff. But when we compared, we can see that total organic matter looks to be derived from within the lake, which means it's driven by productivity. As a result, we said that it's a reflection of macrophytes, which are shallow-rooted plants within our system. And when we have high total organic matter, it means we have an expansion of macrophytes as the lake starts to shallow out. And when we have low total organic matter, we have a reduction of macrophytes as it gets deeper because they require shallow water. And so the picture here shows you Abbott Lake. Our coring site is over here around the bend. And so here, these are these reeds. And when the lake fills up, they reach all into the reeds. But when a lake level starts to lower, it exposes those dead macrophytes. So we see that depending what time we go in the year to Abbott Lake. We also looked at total carbonate, and when we compared it, we found we have low carbonate when GP is absent and a deep lake's inferred, and we have high carbonate when GP is present and a shallow lake's inferred. Now, carbonate can tell you a variety of things as well, but we think it's a reflection of the temperature-solubility relationship. So when we have high carbonate values, it means high epiluminone temperatures, and low carbonate means lower epiluminone temperatures when carbonate dissolution is favored. Lastly, we looked at magnetic susceptibility, and we found that values are uniformly low with no significant trends. And that when we did the isotopic analysis, the del C13 showed really no significant trends, and the del O18 was not really consistent throughout the record when we compared it to other proxies. Because of this, we said that all those three measurements were not really useful in our study and kind of pushed them aside. All right, so to explain all these proxy interpretations, we created a depositional model. And this depositional model has two different modes. The first is sand-on, represented by your deep lake scenario. And during this, you have increased precipitation and runoff when we have these intermittent storms washing through our system. Because we have a higher transport energy, we see high influx of sand. We see low organic matter as we see the macrophytes start to reduce. And we see low total carbonate because that cold runoff washes into our system, cools down our epiluminon temperatures, and favors the dissolution of carbonate. The second mode is sand off, represented by our shallow lake scenario. We have decreased precipitation and runoff, which means we have a low influx of sand because we have a lower transport energy, so we have more fine-grained signal. We have high organic matter, which are represented by those green plants as the macrophytes start to expand. And we have high total carbonate because we don't have that cold runoff washing into the system. All right, so now that we figured out what all of our different measurements meant, we applied them to our statistical groups to figure out how they apply to those groups. And so the record is divided into three major groups. Again, the first one is group 1, being blue. Second is group yellow. And the third is the red group. We did not look at groups 4 through 6 because they only contain 4 atypical values. So we kind of pushed those to the side. And to figure out the three main groups, we first looked at grain size, since that's our dominant signal, and then used the other proxies to help back up those interpretations. All right, so before we get into the groups, you're going to see this figure a lot, so I'll explain a little bit of what's going on. On the bottom here, we have our calendar years BP. We have all of our different measurements. On the left, we have our hydrologic interpretations. The different colors represent the different statistical groups that were determined. And you'll notice that the bottom three records here are all standardized. And the reason we standardized them is we wanted to have a better idea when we were having above or below average situations. And so the black horizontal dashed line for each of those records represents the average of those records. All right. So if we're looking at this, the first group, the blue group, we interpreted it as a wet climate regime with a stable deep lake. And we interpreted it as that because it's characterized by high percent sand, high percent coarse sand, low organic matter, a general absence of GP, and low carbonates. And it accounts for 49% of the total core, so a fair amount. The second group, or the yellow group, we interpret as a transitional environment from deep to shallow. And it was characterized by decreasing sand, decreasing coarse sand, high organic matter, a consistent presence of GP, as well as high carbonate. But it only counts for 10% of the core, not really a lot. Group 3, the last one, we interpret it as a shallow marshy environment when we have a dry climate. And it's characterized by low sand, negligible coarse sand, high organic matter, general presence of GP, and variable total carbonate. And it accounts for 39% of the total core, so a much larger portion. Based on this, we determined that there's 6 periods of increased runoff, or group 1 type sediments, since we determined that that means a wet climate. And the most stable of which is from 1320 to 910, so within this region right here. And that's most stable because we have prolonged period of group 1 type sediments and stability in nearly all of our proxies. Now we wanted to look at the magnitude of this wet interval, so relatively how wet are we talking. So we looked at our coarse sand record. And if we look at our coarse sand record, specifically in this region, we see that when we have the red, or the dry areas, we have very low to absent coarse sand. But as soon as we jump to the blue, or the wet, it jumps up substantially. And when we go back to the red, to the dry, it drops off immediately. So that tells us that these transitions between climate regimes is abrupt. And if we look at the 6 different blue areas, we see that the earlier 3 have much more coarse sand than the more recent 3 pluvials, or extreme wet years. And that tells us that the earlier 3 pluvials are characterized by more intense storms that have a higher transport energy that can wash in more coarse sand than the more recent pluvials. Now if we focus in on the Little Ice Age, so the gray up here shows you the time span according to the IPCC, which is the Intergovernmental Panel on Climate Change. And they say that the Little Ice Age is about 100 to 500 calendar years BP. If we look at this time span, we see that we captured the Little Ice Age from 230 to 155 calendar years BP, so right in this region here. But we notice that it's actually not the most wet period in our entire record, which is kind of unexpected. The earlier pluvials are much more wet than the Little Ice Age at our site. We also find 5 major periods of decreased runoff, the most stable of which is from 770 to 510 calendar years BP. And if we look at the MCA, again, the gray up here shows you the time span, which is about 650 to 1050 calendar years BP. We see that there's a gradual transition to a dry climate as we go from group 1 to group 2 to group 3 type sediment. All right, so now that we had hydrologic variability established, we can then extend the spatiotemporal knowledge of the hydrologic dipole. To do so, we compared Abbott Lake to 2 different records. The first was the Steinman et al. Record from Castor and Lime Lakes in eastern Washington, and it's based on modeled precipitation. The second is a sand record by Kirby from Zaca Lake. And the reason we chose these, well, we wanted to have one that was a little bit closer within this region to the dipole, but there wasn't high enough resolution records to compare to. And with Zaca Lake, it is pretty close to the dipole boundary. There are sites that are more south, such as Lake Elson or Lower Bear, but they didn't have as high enough resolution as Zaca, so we stuck with Zaca. We also didn't compare any of paleoclimate records in that modern transition zone because we wanted to avoid all complexities and only compare records we knew were north or we knew were south. All right, so then this is our figure showing our comparison. We have Castor and Lime Lakes at the top, Abbott in the center, Zaca on the bottom. And they're arranged according to their latitudinal position, so it helps you see it better. So Castor and Lime Lakes north, Abbott's in the center, Zaca's the furthest south. The different colors represent the different hydrologic interpretations, blue being wet, red being dry, green being average. And you'll see that the top 2, Castor and Abbott, are standardized. So you can see that the average is that black dashed line. Zaca's not standardized, but the wet-dry series were established from regime shift analysis done by Kirby. So when we compared all 3, we found that in the highlighted regions, the dipole is between Abbott and Zaca Lake because we see that Castor and Abbott are always in phase, meaning they have the same climate regime at that time, whereas Zaca on the bottom is antiphase, it has the opposite climate regime during those times. During this time period highlighted in red, we see that the dipole shifts north of Abbott between Abbott and Castor because Abbott and Zaca become in phase, Castor is antiphased. A really interesting period, though, happens in the area highlighted by the red dash, and that's because all 3 records are nearly in phase. Castor and Zaca are dry, Abbott Lake is average, so kind of in between. And this suggests either 2 things. 1, the dipole shifted all the way south of Zaca, so that we had phasing between all of them, or that the dipole altogether disappeared. And although it seems kind of crazy, there's times, if you look at past pluvials and droughts, where the entire western United States is arid, specifically the Dust Bowl drought in the 1930s. So it's not unreasonable to suggest that maybe the dipole disappeared at other times in the past as well. But we can't define the dipole for the entire record. All the areas that are not highlighted, we couldn't really say where the dipole is at because there wasn't a clear phasing. Because Abbott Lake is in between the 2 records, it should always be in phase with 1. At these time periods, it's not. So we can't really say where the dipole's at. So what that tells us is that for 960 of the 1450 years we analyzed, the dipole is between Abbott and Zaca. But interestingly, WISE, as we saw in the very beginning of the talk, which seems like forever ago, the dipole has been north of Abbott Lake, right? So in a different position than we see. And so that suggests that the modern dipole she observes is north of its natural average position that we have found. And we think that's due to anthropogenic effects. There's studies that have shown that humans have influenced atmospheric processes over the last 30 years, which could have possibly pulled that dipole north, and that's why she sees more northern dipole than we see over a longer time span. All right, the last thing we did was try to figure out the forcings that are driving hydrologic variability. And we looked at PDO and ENSO. So the top graph is our PDO, Abbott, and our ENSO record. The colors on Abbott, again, represent our hydrologic interpretations. All records were standardized, so the black dashed line represents the average of each record. And the red dashed between the PDO and Abbott shows correlations between the two to help you visualize similarities and differences. We used, for focusing first on the PDO, we looked specifically at the McDonald and Case 2005 PDO reconstruction based on Pinus flexilis trees. And when we did so, we found that positive PDO translated to wetter conditions, and negative PDO are correlated to drier conditions. And that kind of makes sense because a positive PDO, we weaken that pressure system. We have a lower jet stream, so we get more storms. With a negative PDO, we strengthen the pressure system. We have a more northern jet stream, and we have less storms. But it's not 100%. There are some areas where it doesn't necessarily agree. For instance, if you look right here, we have a negative PDO, so it should be dry, but it's wet. And if we look here, we see it goes from negative to positive, so it should go dry to wet, but instead it's just average. It doesn't change. And so because of that, we can say that PDO does play an important role, but there must be additional forcings at work. And that could be solar radiation, it could be volcanic forcings, it could be ENSO, it could be a wide variety of things, but we only focus on ENSO. So if we look at ENSO, which is the bottom graph, we use the Conroy et al. 2008 reconstruction. That's based on a grain size record. But when we compared it, we saw that Abbott Lake was not consistently wet or dry if we had more or less El Niños. It kind of varied and didn't necessarily make sense. So we say that ENSO is not the main forcing, which seems crazy because we hear ENSO a lot. But the thing is, ENSO is more of a Southern California phenomenon. For it to reach Central California, it has to be really strong. And even then, research has shown that the responses aren't always the same in that region. All right, so with that, the Abbott Lake record represents our first paleoclimate reconstruction in the coastal Central California region that spans the MCA and Little Ice Age. And if you look at our hypotheses, we really have three main findings. The first is that we see a dry MCA and a wet Little Ice Age, just as we expected. The second is that we see latitudinal variations in the dipole, and it wasn't stationary. And interestingly, it's further south than we expected it to be for a majority of the record. And the third was partially verified. We thought PDO and ENSO were driving our system. PDO definitely is, ENSO not so much. There could be other forcings at work, but that's beyond the scope of this project. My references. All right, so now that I've babbled for a really long time, probably sick of me talking, that's fine. So, thank yous. So the first one is to Dr. Kirby, who, as he said, I've worked with him for 5, 6, 7, however many years. And he's always been super supportive of me and always there for me, whether it's questions or trying to drive a boat in the lake and making him nearly seasick when the lake had no waves. So thank you for everything you've ever done for me and being patient with me. And yeah. The second is to Dr. Nicole Benuso for all of your work and for running stats on my project twice and helping me figure out what everything meant and all of your efforts in here. I really appreciate it. Third is to Dr. Adam Woods for all of your help in the project and all of you guys for taking the time to read my thesis and be here today. The second set of thank yous is to people who couldn't be here but provided a huge amount of support to this project. The first is Dr. William Barrelson at USC, who allowed us to use his SCM to photograph all of our gastropods. The second is Dr. Saxon Sharp at the Desert Research Institute, who identified the gastropods, since I'm not a gastropod person. And the third is Dr. Bill Patterson at the University of Saskatchewan, say that's 5 times fast, it's fun, who ran isotopic analysis on our gastropods. I would also like to thank Emily, who went with me the first time around to Abbott Lake and the frigid temperatures and helped collect cores and do everything and help run grain size as well. So thank you for everything you did. Jennifer, for going with me the second time around and the third time when I needed someone to help me with the tree line measurements, and for just being there whenever I needed to talk to you so my light bulb would turn on so Kirby didn't have to listen to me every other day. Yeah. More than Kirby probably wants to know. Thank you to the department for everything you've done for me throughout my undergrad and my grad, especially Matt Wilkin, who probably wants to strangle me at times with my technology ghost that haunts me, but's been super patient with me and helping me with everything. And lastly, my family of friends. I couldn't do this without you guys. Whew, emotional train. You guys have been there for me throughout everything. And wow, that's enough. Okay, you get it. All right. Well, we're almost done. All right, so only because I have to, are there any questions?